I'm going to play this movie, and it's going to show the discovery of exoplanets over time, demonstrating the rapid pace of discoveries that this field has experienced over the years. So as the planets start popping on the field, the circles here represent their location on the sky, and the size of the circles represent the relative size of their orbits. You can start seeing them pop all over the sky. The color of these circles determines the detection technique that was used to discover these planets. There's a musical tone in the background that might be difficult to hear, but it's sonified to essentially demonstrate what the orbital period of these planets would be. You could see there was a rapid pop of thousands of planets being discovered in one patch of sky over there. That was by the Kepler Space Telescope. So wow, it's been nearly 3 years since we reached the 5,000 exoplanet mark. And since then, now we have reached almost 6,000 plus exoplanets. But among these 6,000 exoplanets, one planet is still missing, an Earth-like analog orbiting a sun-like star outside our solar system. And this is the planet that we really want to find, that is tied to the ultimate goal of exoplanet astronomy, the search for life outside the solar system. The direct imaging technique is the technique poised to accomplish this extremely challenging task. What we want to do is image an Earth-like planet orbiting a sun-like star, much like the famous pale blue dot image that was unveiled by Carl Sagan. What we want to do after taking a picture of such a planet is to obtain a spectrum, its brightness as a function of wavelength, to look for molecular signatures of life in its atmosphere. In fact, NASA is working on a space telescope called the Habitable Worlds Observatory, poised to launch in the next 2 decades or so, which is purpose-built to detect these Earth-like planets and characterize their atmospheres, searching for signs of life. Where would we point such a telescope? In selecting the optimal targets to search for Earth-like planets, the distance to these planets matters. So for example, if you have an Earth-like planet orbiting a sun-like star, the further away the star-planet system is from us, the smaller the separation between the star and planet looks from our perspective on the sky, which means it's easier to detect planets around our nearest stars, where the planet-star separation is large enough for us to be able to disentangle the planet light from the starlight when doing direct imaging. In fact, planets that are closer to us will be brighter, making this even more advantageous to look for planets around our nearest stars. Alpha Centauri is the closest star system to planet Earth. It is the most favorable target to search for exo-Earths orbiting other stars. Here is a famous image from Hubble showing the two sun-like stars in the system, Alpha Centauri A and B. There's a third star in the system called Proxima Centauri, but it's much further separated from these two stars. You can see Alpha Cent A is slightly bigger and brighter. It's slightly more massive and bigger than the sun, whereas Alpha Centauri B is slightly less massive and smaller than the sun. The Alpha Centauri AB orbit is quite eccentric. So here's an illustration showing what the orbit of Alpha Centauri B around A looks like in comparison to the planets in our own solar system. So you can see at closest approach, Alpha Centauri B is almost at similar distance as Saturn is from the sun. And at furthest approach, it's further out than Uranus is from the sun. This eccentric close orbit is actually quite hostile to the formation of planets, which requires a dynamically stable environment for dust and rocks to stick together and form the cores of giant planets as well as the terrestrial planets. However, in spite of this hostile environment, various studies have shown that the habitable zone around both of these stars would be dynamically stable on long time scales to the presence of the other stars. So this illustration shows in green the extent of the habitable zone around each star. In the case of Alpha Centauri A, it spans from 0.8 to 2.4 astronomical units, where 1 astronomical unit is the distance between the sun and the Earth. And that's shown for reference as a dashed line. And in the case of Alpha Centauri B, the habitable zone extends across a smaller range of distances from 0.5 to 1.4 astronomical units. So presently, we do not have the telescopes to search for Earth-like planets in the habitable zone of Alpha Cent A. But there is a very unique opportunity offered to us by NASA's most powerful space telescope, the James Webb Space Telescope, to search for giant planets like Jupiter and Saturn in the habitable zone. So here I'm showing you the brightness on the y-axis as a function of wavelength of light or color of light for the sun in blue and for a Jupiter-sized planet in the habitable zone of Alpha Centauri A in yellow. So you can see that at the shorter wavelengths of around 1 to 2 microns, the planet is significantly fainter than the star. Whereas the longer in wavelength you go, or the redder in color you go, the brightness between the star and the planet becomes more comparable, easier for detection. Looks like the Dodgers are winning. So if I look at what space telescopes we have, or ground-based telescopes we have to study or search for planets around Alpha Cent A, the Hubble Space Telescope was built to look at the shorter wavelengths, so it's not really optimal to search for planets around Alpha Cent A. Nevertheless, it was used as early as 1999 to try and search for potential planets. The Keck telescopes in Hawaii, which Caltech manages, can study the wavelengths intermediate at roughly 3 to 4 microns, but that's not the most optimal range. The most optimal range are at these longer wavelengths, where the only telescope capable of imaging planets is the James Webb Space Telescope, specifically an instrument called the Mid-Infrared Instrument, or MIRI, on board. So we used the James Webb Space Telescope with the MIRI instrument to try and search for giant planets in the habitable zone of Alpha Centauri A. This is the first image we took of the system. You can see the 2 stars outshining everything else in the field, with the telescope's famous 6-fold diffraction pattern. So the stars are extremely bright. It's very difficult to search for planets in their glare. We need to use a specialized device called a coronagraph to block out the starlight and search for planets. So a really cool analogy as to what a coronagraph does is that during the daytime, the brightness of the sun hides the planets in the solar system. The planets are actually up in the sky during daytime. But in the rare event of a total solar eclipse, the moon acts like a coronagraph, blocking a lot of the starlight and revealing faint planets, such as in this case, Mars in the background. So this is an actual image taken during a total solar eclipse, which happened during daytime. Yeah, we all love total solar eclipses. You should definitely go and see the next one upcoming in 2026. Okay, so let's create our own total solar eclipse for Alpha Centauri A. If we block the starlight using a coronagraph on board JWST, we get this really beautiful image of a spoke-like pattern where you can see at the center Alpha Centauri A blocked by the coronagraph. What you're seeing is 1% of the residual starlight still leaking through and creating this pattern. However, since there's only one coronagraph on board JWST, you cannot block the light of Alpha Centauri B, which is why it is extremely challenging to search for planets around our nearest star. Alpha Centauri B is there contributing its full brightness on our detectors. So we need to be able to subtract out all of this light to search for a tantalizing signal within this ordered chaos of diffraction. So to do that, we employ a strategy where we observe a star called a reference star. This is a star different from Alpha Centauri AB that's nearby on the sky, but it's quite a boring star. We know there are no detectable planets around it. What we do is we observe this reference star in the same position that we see Alpha Centauri A and B. So on the left is our image with JWST of Alpha Cent A behind the coronagraph and Alpha Cent B off to the side. And on the right is this boring reference star that we have also observed behind the coronagraph. So you can see that we have obtained a matching pattern for the starlight for Alpha Centauri A. Similarly, we can place the reference star at the position of Alpha Centauri B on our camera and obtain a matching image as that. And once we get these matching images, we can subtract them out from our science image of Alpha Cent AB to remove any of the contaminating starlight. So if we do this, we find a tantalizing signal, a point-like source that we find to be a candidate planet orbiting Alpha Centauri A that's almost 20,000 times fainter than the star itself. So first we had to filter out 99% of the light with the coronagraph, and then using clever PSF subtraction algorithms, we are able to remove most of the remaining light to get down to the sensitivities to search for giant planets in the habitable zone. Now what's very interesting is that there was a ground-based observing campaign with the very large telescope in Chile managed by the European Southern Observatory called the New Earths in Alpha Cent experiment, the NEAR experiment. It observed Alpha Cent A over several nights for over 100 hours and obtained a signal, candidate tentative signal, which they called C1 in 2019. Why is this signal very interesting? It's very interesting because we believe that this could be the same object as the S1 detection that we see with JWST, but on the other side of the star. So motivated by this, we decided to use JWST 2 more times to try and recover this candidate planet and test if the signal was real. We observed it in February 2025, and then again in April 2025. But we did not see any signals comparable to the S1 source that was detected in August 2024. Does this mean it's not real? Where did the planet go? So to investigate this, we simulated orbits between the two possible detections, S1 and C1, that we saw on the opposite sides of the star. And this is what the orbits look like on sky. I've shown 100 random orbits drawn from our computer simulations. The planet, potential planet, was seen in June 2019 at the C1 position, and then was seen in August 2024 at the S1 position. Based on these orbits, we infer that the orbital period, or the time it takes for the potential planet to revolve around its star, is about 2 years. Based on that, if we project forward in time the position of the planet, both in February and April 2025, the planet would be moving closer to the star towards the C1 position, and in fact, it would be too close to the star for JWST to be able to detect it. About 50% of the orbits were consistent with the fact that we did not see it in the JWST observations. So in fact, it is entirely possible that we missed this planet because of orbital motion. Nevertheless, the definitive confirmation has to come from a redetection of this candidate in a second epoch with the same instrument. Apologies. What's very interesting from the orbit analysis is that we also find that the candidate planet's orbit would be tilted with respect to that of the Alpha Centauri AB binary orbital plane. And typically with binary stars or planets in binary systems, we have found that the planets are generally aligned with the orbital plane of their binary stars. And this points to the fact that this particular planet might have undergone a chaotic formation and evolutionary history to find itself in this present state. What else do we know about the properties of this planet or potential planet? So as Caitlin mentioned, we have the radial velocity technique, which can search for wobbles in the star due to the presence of a planet. There have been decades of radial velocity observations searching for planets around this famous star, but none have found any. Essentially, we can tell that the planet has to be about the mass of Saturn, because if it was more massive, then it would have been detected in previous radial velocity observations. The brightness of the planet that we measure from our image with JWST also helps constrain what the possible mass of this planet might be. We know that the planet's temperature would be roughly around minus 50 degrees Celsius, or roughly Fahrenheit as well. And that's because it's located near the outer edge of the star's habitable zone. So we can balance the heating from the star by the cooling of the atmosphere of the planet to calculate the equilibrium temperature of this particular planet. Finally, together with the temperature and the brightness of the planet, we can infer that the size of the planet would have to be similar to that of Jupiter. Now, the planet's orbit is also found to be roughly eccentric, so it's sweeping the habitable zone all the way from 1 astronomical unit to 2 astronomical units. This doesn't really bode well for the presence of Earth-like planets in the habitable zone if this planet is confirmed, because like a bowling ball, a giant planet barreling through the habitable zone would knock out any rocky planets, or would even in the worst case prevent the formation of one in the earlier stages. However, this does not exclude the possibility that there could be moons around this potential planet. We know that all of the gas giants in our solar system have a lot of moons orbiting them. So it raises interesting questions if this planet is confirmed, whether there are moons, and if so, could any of them be habitable? So what's next for the Alpha Centauri system? So our first priority is to confirm this potential planet with JWST, and we have identified that the best opportunity to do this is next year in August. So if you remember, I mentioned that the orbital period is about 2 years, and we detected the candidate at the S1 position in August 2024. So 2 years later, that is August 2026, we expect the potential planet to arrive at the same location or be detected the same location in follow-up observations. So we have submitted a proposal to try and request for time to make this confirmatory observation. In the near future, the Roman Space Telescope has a direct imaging mode that's been led by JPL that could potentially detect this planet at optical wavelengths, the visible light wavelengths that we see, by looking at the light reflected by the planet from its host star. That could characterize the planet's reflectivity and probe for the presence of water clouds. And the Ptolemy Space Telescope, also set to launch in the next few years, could measure the gravitational tug of this planet on its star and measure a mass for the planet. Finally, if you want to search for moons around this planet, if confirmed, our best bet would be the Extremely Large Telescope, or the European Extremely Large Telescope. This is going to have a 40-meter primary mirror in diameter. The current biggest ground-based telescopes have a primary mirror of about 10 meters in diameter. So almost 4 times larger, which allows us to detect fainter planets at smaller separations from their star. So we can use the radial velocity technique on the planet, as Caitlin mentioned, to try and search for the tug of a moon on this potential planet. So in the meantime, this particular potential discovery is very exciting for the field of exoplanets. If this candidate S1 is confirmed as the planet Alpha Centauri AB, it would break records, making it the nearest, coldest, oldest, lowest mass, shortest period planet to be imaged orbiting a sun-like star to date. It would open the doors to characterizing the atmospheres of gas giant planets more similar in temperature and age to the Jupiter and Saturn in our own solar system. So if space is the final frontier, then humanity's first destination surely has to be the closest sun-like star, Alpha Centauri A. Film and TV has imagined a diversity of wonderful worlds around this fascinating star system, even before the potential discovery of one. So as we've been alluding to, we have seen in the Avatar movies, the gas giant Polyphemus orbits in the habitable zone of Alpha Centauri A and is host to the moon Pandora. We have the Cybertron planet in Transformers, also around Alpha Cent A. We have Trisolaris, a world which experiences an endless cycle of chaotic and stable eras, also in the Alpha Cent system. And then finally, a planet called Alpha Centauri, which was the destination of Lost in Space's adventurous Robinson family. Not to mention the numerous books that wrote of these worlds even before we saw them on the big screen. So in a truly remarkable coincidence, legendary science fiction writer Arthur C. Clarke's famous 1958 short story, Songs of Distant Earth, actually describes mankind's journey to a planet called Pasadena, orbiting in Alpha Centauri A, obviously named after our home and the home of Caltech and JPL, the two institutions leading this potential discovery. So will we find the Pandora to our candidate Polyphemus? This is the question James Cameron asked me. And while the answer for that will have to wait, what's sure is that we are slowly beginning to build a bridge between our vivid imagination and reality. Thank you, and I'm happy to take any questions.